Hello everyone, thanks for attending for the presentation. My name is Huang Xianyang. The topic of my presentation is memory optimization in deep learning. And my presentation will develop in these four parts. First, let's pay attention to research background. With the advent of the era of AI, deep neural networks are widely used in various practical fields. At present, deep learning has been used in face recognition, autonomous driving, robotics, and other fields. And the application of deep learning has significantly improved the current human life. The structure of neural network model is becoming more and more complex. However, the limited memory capacity of GPU has become the main bottleneck limiting the scale of neural network models. To date, the new NVIDIA GPU V100 only has a maximum of 32 GB of memory, which is far from enough to accommodate deep neural networks. For example, the latest Inception V4 model has 515 layers and requires as much as 44 GB of memory during the training process. So, how to effectively use GPU memory resources and maintain good performance is an urgent problem to be solved. Next, let's talk about related research. At present, there are two representative memory optimization methods, CPU-GPU transfer and recompute. CPU-GPU transfer method introduces a large capacity CPU memory as a virtual memory pool of the GPU, which expands the storage space of the data during training process. This method transfers the data that do not participate in the current calculation to the CPU memory, reduces the GPU memory consumption of the neural network, and alleviates the shortage of GPU memory capacity. The compute method is a typical application of time for space idea, which uses the strong computing power of GPU to exchange for the limited memory space. Compared with the normal iterative calculation that includes one forward calculation and one backward calculation, the compute method only has one more forward calculation. So far, there has been a lot of studies that apply CPU-GPU transfer or recompute alone to optimize memory management. Let's first talk about the researches on CPU-GPU transfer. Who proposed a virtualized deep neural network called VDNN. VDNN virtualizes the memory usage of neural networks between main memory and GPU memory. Feature maps reside in GPU memory for a long time as an intermediate data structure and consume a large amount of GPU memory. Therefore, during fault propagation, VDNN exchanges the feature map to the main memory, thereby reducing the occupation of GPU memory. Jin proposed an interlayer memory reuse strategy based on CPU-GPU data transfer. This strategy records the memory access sequence of each layer of data in the GPU and tracks the count of data referenced by other layers. In this way, the sequence of memory accesses for the training process can be established to determine when to transfer data. This method can effectively reduce the performance loss. For recompute method, Chen proposed the gradient checkpoint algorithm. Specifically, the neural network is divided into several parts, and the algorithm only returns output results of each part. Removing all intermediate results, the memory space required by this algorithm includes the memory space for storing each part of the output results and the memory space required for each part of the backpropagation calculation, which reduces the memory occupied by extra forward calculation. Ruthless combines the idea of recompute with a backpropagation through time algorithm and proposed a method to reduce memory consumption when training RNNs. The method uses dynamic programming to balance the caching and the recalculation of intermediate results enabling the training of neural networks under any memory constraints specified by the user. Now, we enter the model design and analysis stage. As some previous research suggests, a CPU-GPU transfer method and the recompute method both cause serious performance reduction while optimizing the memory consumption of neural networks. But the causes of performance reduction caused by these two are different. Compared with a normal iterative calculation, the recompute method has one more forward calculation, which brings a performance drop of 25%. The performance reduction of the CPU-GPU transfer is caused by data transmission between the GPU and the CPU. Therefore, I wonder if I could combine these two methods to design new mechanism to optimize memory. So next, in order to show that recompute method and the CPU-GPU transfer method have different performances on different types of layers, in this section, I take the AlexNet model as an example to compare the performance differences between these two methods. As can be seen from the figures, on the convolutional layers and the fully connected layers, the performance of CPU-GPU transfer method is better, but on activation layers and the pruning layers, the compute method is better. And the reason for the difference in performance is that different layers have different computing and memory requirements. Operations for convolutional layers and fully connected layers are essentially matrix multiplication, which requires higher computing resources and is usually considered to be computationally intensive. The other layers, such as activation layers, require less resources in computation, but its memory requirement cannot be ignored. So in this case, it is necessary to classify the layers in the neural network and divide them into calculation-sensitive and transfer-sensitive types, according to the relation between the computational cost and the transfer cost. In general, a threshold of 2 is a significant watershed. When a threshold is less than 2, the current layer is calculation sensitive, otherwise the current layer is transfer sensitive. Now, let's talk about the implementation. The strategy selection mechanism will be implemented in 2 steps. The first step is to calculate the data transfer cost and the extra forward computation cost of each layer in the neural network, and mark each layer as transfer sensitive or computation sensitive according to its threshold. The second step will be a little more complicated. For calculation sensitive layers, during the forward propagation process, the input feature map of the current layer is transferred to the CPU memory. During back propagation process, feature maps temporarily stored in CPU memory are prefetched. Among them, the data transfer process between the CPU and GPU is performed in parallel with the normal iterative calculation process. For the transfer-sensitive layer, in the forward propagation process, the input feature map of the current layer is discarded. It should be noted that the corresponding memory block is not actually released at this time, but is marked as free and reused by the next feature map. During the back propagation process, extra forward computations are used to recover the discarded feature map. The last section is results and future work. In order to verify the effectiveness of the strategy selection mechanism, the test selects 2 existing single memory optimization methods, recompute and CPU-GPU transfer, as the comparison objects. Next, test and comparison are performed on a series of representative neural network models, including AlexNet VGG16, GoogleNet, ResNet34, ResNet50, DenseNet 121, and Inception V4. Using the original training time as a baseline for comparison, the execution time of the 3 methods is tested separately. In the fig, the three bars represent the execution time of the strategy selection mechanism, CPU-GPU transfer, and recompute. It can be seen that for different models, the performance of recompute and CPU-GPU transfer have their own advantages and disadvantages. And to be specific, on the ResNet 50 and the DenseNet 121 models, recompute method outperforms CPU-GPU transfer method. On the BoogNet model, the performance overhead of these two is comparable. But on other models, CPU-GPU transfer method is better. However, compared with these two methods, the execution time of the strategy selection mechanism is the shortest on all models. The reason is that compared with the recompute and the CPU-GPU transfer that uses a single optimization method for all layers in the neural network, the strategy selection mechanism is able to select the appropriate optimization method for each layer in the neural network, which can achieve better training performance. In addition, the extra performance overhead of different memory optimization methods is shown in the table. It can be seen that the strategy selection mechanism outperforms the recompute and the CPU-GPU transfer in terms of minimum, maximum, and the average extra performance overhead. And current studies have shown that using the strategy selection mechanism can effectively reduce the execution time of the training process of deep neural network, but the GPU memory usage is not considered. Therefore, the next step is to study the memory consumption during the training process and analyze and optimize the GPU memory occupation of intermediate data generated in the training process. Thanks for your listening.